Today we're going to talk about reference angles and triangles in circles. For an angle theta in standard position, the reference angle, theta prime, is the positive acute angle formed by the terminal side of theta and the shortest angular distance to the x-axis. So to find the reference angle, you want to draw the angle in standard position, create a triangle, draw a vertical line from the terminal side to the x-axis, and then find the acute angle formed. It may be part of the given angle or it may be outside the given angle, and that is your reference angle. It's also important to note down here that if the given angle theta is negative or it's greater than 360 degrees, first I would find the coterminal angle from 0 to 360 and then find the reference angle. And of course, if you're using radians, that would be from 0 to 2 pi. So if we look at these pictures that we have here, remember this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So in the first quadrant, if the angle that you're given is in between 0 and 360, that means that you have your acute angle. That means theta prime, which is the reference angle, is equal to theta. So this would be your reference angle and the given angle. If you're in quadrant 2 for your terminal side, such as in the second picture, we know that this from here to here is the angle drawn in standard position. So the reference angle is going to be this angle right here. So how do we find that? If we're in the second quadrant, you do 180 degrees minus the given angle, or if you're using radians, pi minus the angle. Looking at the next one in quadrant 3, so for this one, the given angle theta goes from here to here. So the reference angle would end up being this angle right here. So how do we find it in quadrant 3? You take the given angle and subtract it from 180, or you take the given angle and subtract it from pi. And when you are in the fourth quadrant, so if this was the given angle, then right here would be the reference angle, because again, remember the reference angle is the positive acute angle formed by the terminal side of theta and the shortest angular distance to the x-axis. So in this quadrant, we're using this x-axis here, which is 360, so 360 minus theta or 2 pi minus theta to find the reference angle. So let's go ahead and just look at some of these. So for the first ones, it says draw each angle in standard form, then find the measure of the reference angle. So for this, 48 degrees, we would know would be somewhere about here. So this right here would be the angle drawn in standard position. So that means that because we're in quadrant 1, that the angle of theta is equal to the reference angle theta prime, which is equal to 48 degrees. So up here, theta equals theta prime. So in the next one, we have 122 degrees, which would be in quadrant 2, because remember again, this is 0 degrees, 90 degrees, 180 degrees to 70 degrees, and back all the way around is 360 degrees, which we've talked about. So 122 degrees would be about somewhere up here. So the angle drawn in standard position would be here, which is theta. So that means that this angle right here would be theta prime. So to find the reference angle, because we haven't gone past 180 degrees and we always use the x-axis, we take the 180 degrees and subtract it from the angle that was given, which is 122 degrees, which ends up giving us 58 degrees for the reference angle. Looking at the next one, we have 215 degrees, which we know is in quadrant 3. So 215 degrees would be about somewhere in here. So from here to here is theta, and the reference angle is going to be this angle right here. So to find the reference angle theta prime, because we've gone past 180, we take the given angle, 215 degrees, and subtract it from 180 degrees, and that gives us a reference angle of 35 degrees. And the last one we can see is in quadrant 4. So 304 degrees would be about somewhere in here. So that would be drawn in standard position looking like this. And the reference angle for this would be here. So theta prime, because we're in quadrant 4, hasn't quite reached 360, so we take 360 degrees and subtract that from 304 degrees, which gives us 56 degrees. And that would be our reference angle. So even just to look at another visual, you can see here in the first quadrant, your reference angle, if you're in between 0 and 360, is the given angle. In the second quadrant, notice that, again, the blue is the standard angle and the red is the reference angle. So when we had about 122, we get that's 58 degrees. And when we are in the third quadrant, we had 215, which gives us a reference angle of 35 degrees. And notice again, your triangle is being always made with the x-axis. You don't ever make your triangle with the y-axis. It's always the x-axis. So when we get over here into quadrant 4, same thing, triangles being made with the x-axis. And we had, for this one, I think it was 304 degrees. So 304 degrees gives us 56 degrees for our reference angle. So this kind of just gives us a visual of what the given angle is and what the reference angle would be. And again, notice the right triangle is always being made with the x-axis. So in quadrants 1 and 4, it's made with the positive x-axis, and in quadrants 1 and 2, you're making the triangle with the negative x-axis. So if we have an angle that is above 306 degrees or a negative angle, we would first want to find our coterminal angle with 585 that is between 0 and 360. So remember to find your coterminal angle. You add or subtract 360 degrees depending on the angle. So in this case, if we have 585 degrees and we subtract 360 degrees because it's over 360, we get 225 degrees. So we know that 225 degrees is in quadrant 3, again, because we know this is 90 degrees, 180 degrees, 270, and all the way around would be 360 degrees. So 225 would be right here in the middle. And when we're drawing the angle in standard position, remember we're not drawing the coterminal angle, we're drawing the 585 degrees. So that's 360 plus 225 to get 585. So we have to go all the way around once. And so remember, if you start at the x-axis and go counterclockwise, that stands for a positive angle measurement. So that would be 360 degrees plus an extra 225. That gives me my angle of 585 degrees. So then the next thing that we need to do is find the reference angle, and we're going to use the 225, which is coterminal with the 585, to help us. And so remember, the reference angle again is the positive acute angle made with the terminal side and the shortest angular distance to x-axis. So this right here is going to give me my reference angle. So we need to figure out what that angle measurement is right there. So theta prime is going to be equal to, since we've gone past the 180 degrees, we take the angle, which is 225 degrees, and we subtract 180 degrees, and this gives us 45 degrees. So that means that that is my reference angle. For question 13, we have theta is equal to negative 400 degrees. So to find the coterminal angle, we're going to add 360 degrees to that. So when we add 360 degrees, we get negative 40 degrees, which is still negative. So we're going to take that answer and add another 360 degrees because we want our answer to be positive in between 0 and 360, which gives us 320 degrees. So that tells me I'm in quadrant 4. So 320 degrees would be about somewhere in here. But remember, the angle we're drawing in standard position is negative 400 degrees. So if I'm drawing negative 400 degrees, I've gone all the way around this way is the negative direction to my terminal side. So that's the angle drawn in standard position. And then the reference angle, of course, is going to be this angle right here. So theta prime is equal to, since we're in the fourth quadrant, we're going to take 360 degrees and subtract it from the 320 degrees, because remember, you always want to use the angle between 0 and 360 when we're doing this. So that means that theta prime, or the reference angle, is equal to 40 degrees. Now, if we look at question number 14, we're given a radian measure. So if you don't know where the radian measures are on your graph, you can always change this into degrees by multiplying it by 180 over pi. Remember, that's what we use to go from radians to degrees. When we do that, we get 252 degrees. So 252 degrees tells me I'm in quadrant 3. So our graph would be somewhere about down here. So it's positive, so we're going from here to here is theta. My reference angle is going to be this angle right here, theta prime. Since our given angle is in radians, we want to have our reference angle in radians. So theta prime is equal to 7 pi over 5 is 252, so that's in between 0 and 2 pi. So we can take the angle that we're given, because we're in quadrant 3, 7 pi over 5, and subtract that from pi, because again, we are using this picture right here. So theta minus pi. So 7 pi over 5 minus pi means we need to get a common denominator. Whoops. So if I get a common denominator, I'm going to multiply this by 5 over 5. So when I do, I get theta prime is equal to 7 pi over 5 minus 5 pi over 5, which gives us 2 pi over 5. So theta prime equals 2 pi over 5. Could you have also taken the angle in degrees and got that answer and then changed it into radians by multiplying by pi over 180? Sure, that would also work. Two different ways of doing the problem. So looking at question number 15, same thing, multiply this by 180 degrees over pi to put it in degrees, so the pi's here would cancel out. And when you simplify, you would end up with 110 degrees. 110 degrees tells us we're in quadrant 2, which would be somewhere about up here. So this is our angle of theta. So theta prime, our reference angle, would be here. So since we're using radians, I'm going to use radians to help. We haven't gone past pi or 180 in this case, so here's again pi. So that means we're going to take pi and subtract it from our given angle, 11 pi over 18, which means I need to get a common denominator to add these, so multiply this by 18 over 18. And when we do, 18 pi over 18 minus 11 pi over 18 gives us 7 pi over 18. So that means that's my reference angle. And again, you could do this using the degrees and then just convert it back into a radian measure. That's fine. So that is how we find reference angles. So we're going to use these to help us with the next part. All right, so for this next part, we have George W. Ferris's day off. Perhaps you have enjoyed riding on a Ferris wheel at an amusement park. The Ferris wheel was invented by George Washington Ferris for the 1893 Chicago World's Fair. Carlos and Carlita and their friends are celebrating the end of the school year at a local amusement park. Carlos has always been afraid of heights, and now his friends have talked him into taking a ride on the amusement park Ferris wheel. As Carlos waits nervously in line, he has been able to gather some information about the wheel. By asking the ride operator, he found out that the wheel has a radius of 25 feet and its center is 30 feet above ground. With this information, Carlos is trying to figure out how high he will be at different positions on the wheel. So the first question says, how high will Carlos be when he is at the top of the wheel, To make things easier, think of its location as simply a point on the circumference of the wheel's circular path. So if we look, if we want to figure out how high we are at the top of the wheel, that would be here. So we have to think about our given information. So it told us that the wheel has a radius of 25 feet. So that means from here to here, I know is 25. I also know from here to here is 25. And it also told me that the center of the wheel is from here to here, right? Because it would be from here to here, is 30 feet above ground. So knowing that, to find how high we'll be at the top of the wheel, we can take the fact that we know the center is 30 feet off the ground plus the radius of the wheel, which is 25. So that's again the how high off the ground from the center. And the radius. So when we add those together, we get 55 feet. So that tells us that the highest point is at 55 feet. So the next question says, how high will he be when he is at the bottom of the wheel? So that would be this point down here. So if we know that from the ground to the center of the wheel is 30 feet and the radius of the wheel is 25 feet, then that should be easy to find this little piece of information right there for how high we're off the ground. So we just take the fact that we have 30 minus that radius 25, which tells us we are 5 feet off the ground. So the next question says, how high will he be when he is at the positions farthest to the left or farthest to the right of the wheel? So farthest to the left would be here and farthest right would be here. And of course, those are the same height as the center of the wheel. So that tells us he'll be 30 feet off the ground. So he will be 30 feet off the ground because it's the same height as the center of the wheel. Because the wheel has 10 spokes, Carlos wonders if he can determine the height of the positions at the ends of each of the spoke as shown in the diagram. Carlos has just finished studying right triangle trig and wonders if that knowledge can help him. And what a coinkydink, we've just finished our right triangle trig review as well. So let's go down here. So it says, find the height of each of the points labeled A through J on, it should say, the Ferris wheel diagram below. Represent your work on the diagram so it is apparent to others how you have calculated the height at each point. So we already know that A from here all the way down to the ground is 30 feet because that was given to us. So that means F is also at 30 feet because again that was given to us. So how can we figure out what the height of each of these different values is going to be? Well, first of all, we need to figure out what each of these angles are going by, right? So how can I figure out what each of these different angles are in between each of the spokes of the wheel? So take a minute to pause the video, and when you're done, unpause the video to check your work. So remember that if the whole wheel has 360 degrees, then you can count how many different sections we have. So one, if we start here, this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 different triangles around. So that means to find theta, theta would be equal to 360 degrees, which is the whole, divided by 10 different parts, which gives us 36 degrees. So that tells me that this is 36 degrees and all of those triangles are 36 degrees. So how can I find the height of B? Again, because they told us we're going to use right triangle trig, using some right triangle trig. So see if you can pause the video to figure out if you can find what the height of B would be. Here we're trying to figure out what the height is from B all the way down to the ground. So if we look at this triangle right here, notice that makes a right triangle. And we know the hypotenuse of the triangle is the radius of the wheel, which we were told is 25 feet. So we know from the ground to the center is 30 feet. We've already talked about that. So how can we find this distance from here to here using our right triangles? So that is the opposite of the given angle, and we have the hypotenuse. So if it's the opposite and hypotenuse, then that means, remember, we have SOHCAHTOA. So sine is opposite and hypotenuse, so I can use my sine function to help me. So the sine, we're doing the B point here. So the sine of the angle 36 degrees is equal to, we're trying to find, I'm going to call that h for height, so h over 25. So in order to solve, multiply both sides by 25. So h is equal to 25 times the sine of 36 degrees. And all we have to do is plug that into our calculator. So if I get my calculator, the first thing I want to do is make sure my mode is in radian mode. And if it's not, just use your down arrow and hit enter on radian. Or not radian, sorry, degrees. I'm thinking in my other class. So degree mode, because we're doing degrees. So if it's not, make sure you change that. And every time you clear your calculator memory, always defaults to radian. So second mode gets you out back to the home screen. So 25 times the sine of 36 degrees, enter, and we get 14.69. So that is h. But remember, that is not the actual height off the ground. We have to add 30 to that. So 14.69 plus the 30 gives us a height of 44.69 feet. So B is 44.69 feet above the ground. So looking at your triangle, you'll notice that it has some symmetry. So we can think of this as triangle. Think about if you were to reflect it across, if there was a y-axis. Notice that it would match up with this triangle right here. And so that means that B and E are at the same height, right? So this is also 44.69 feet. Well, again, thinking about symmetry, that triangle, if we were to flip it across the x-axis, would match up with this triangle here, and on the other side, this triangle here. So now we need to figure out again what the distance off the ground is. So how do we figure out the distance off the ground? Well, we know that this green line we found from before was 14.69, right? So this is 14.69. And the distance from the ground to the center is 30. So for points G and F, or no, sorry, G and J, we can take the fact that we know that the center is at 30 and subtract it from the 14.69. And when we do, we get the height off the ground, which is 15.31 feet. So that means this height is 15.31 feet. And this one is also 15.31 feet. So now we're almost done. We just have to do C, D, and H, and I. So see if you can pause the video to do those on your own, and when you're done, pause the video to check your work. All right, so now we're looking at trying to figure out the height of C from the ground. So that would be this distance from here to here. So notice that when we do that, that creates, again, a right triangle right here. So basically, we need to figure out what the angle standard position would be from here to here. So if one triangle is 36 degrees, which we already knew, I'm going to erase that right there, then from here to here would be 36 plus 36, which is, of course, 72 degrees. And we know this is a right triangle. And of course, from the center to point C, that's the radius, which is 25 feet. So if we figure out this distance from C to the center of the wheel, we can add 30 to that to figure out how high C is from the ground. So we're going to use our right triangle trig again. So we have 72 degrees, and if you want to make your triangle over here, so it makes it a little bit easier, so 72 degrees, and this is 25, and we're trying to find H. So when we do opposite and hypotenuse, we're using our sine again. So the sine of 72 degrees is equal to H over 25. So H is equal to 25 times the sine of 72 degrees. So we can use our calculator, again, making sure you're in degree mode. So 25 times the sine of 72 degrees. Didn't do the 25, I accidentally did 2. So let's try that again. So 25. And that gives us 23.78 feet. So of course then we can take that and add the distance, which is from here to the ground. We know from the to the center is 30. So if we add that 30 to that answer, we get 23.78 feet plus 30 feet, which gives us a total distance of 53.78 feet. So 53.78 feet. And again, just like the other triangles, we have symmetry with D. C and D are using the same triangle. So those are going to be at the same height, 53.73 feet. And we can see that if we were to flip our triangle over the x-axis, that H and I also use the same triangle. So we can use that to help us figure out the distance of H and I off the ground. So we know that this distance, again, from here to here, we said was 23.78. So if we know the total distance from here to here is 30, we're just going to subtract. So for H and I, we take 30 feet and subtract it from 23.78 feet. So that gives us 6.22 feet above the ground. So this would be 6.22 feet and 6.22 feet. And that gives us all of the heights of the different points on our Ferris wheel just by using our right triangle trig and some knowledge of what the radius of the wheel was and how high off the ground the center of the wheel is. And that's it, and we'll be using this idea for some of the next few lessons as well.